So far, we've looked at analyzing data for one mean, for two means, for one proportion, for two proportions. But now we're going to kind of shift gears and say, okay, well, what if I have more than that? Like one was fun, two was funner, but what about three or more? Can I compare three or more proportions or three or more means? And the answer is yes, we can. But of course, it's going to get a little bit complicated as we start having more and more things that we're comparing here. So when we are doing all these extra comparisons here, we're going to have to take a little bit different of an approach. Because if you can imagine, if we're comparing like 5 proportions, like how do we compare those? Do we do a bunch of pairwise tests? Do we just kind of look at them somehow all together? And it's tricky to do a bunch of pairwise tests to see if anything's different from each other, because then we get into the problem of multiple testing, where when we do lots and lots of tests, we expect some are going to be significant just purely due to chance, as we talked about back in section 4.4. So what we're going to do with these multiple comparisons, comparing multiple proportions or multiple means, is we're going to follow kind of a two-step strategy. And our first step is going to be to do an overall test. And the overall test is going to look and see if there's any differences among any of the proportions or among any of the means, depending on which test that we're doing. And then if that overall test is significant, then we're going to dig deeper, do a follow-up analysis, and see exactly where the differences are. So that's going to help with making errors with that multiple testing and things like that. So our first step, do an overall test, see if there's any differences. Second step is if that overall test is significant, then we're going to do a follow-up analysis to see exactly where those differences are. And in chapter 7 here, we're going to be looking at categorical variables, so doing multiple comparisons for proportions, essentially. And then in chapter 8, we're going to be looking at comparing several means. And our basic strategy, this two-step strategy here, is going to be the same for both chapters. All right, so to kind of help us understand how this is all going to work, we're going to use this example here. So this says the popularity of computer, video, online, and virtual reality games has raised concerns about their ability to negatively impact youth. Although the existing literature has been inconsistent, the data in this exercise are based on a recent survey of 14 to 18-year-olds in Connecticut high schools. Here's the grade distributions of boys who have and have not played video games. So we have this data here. We have kids who've played video games, people who've never played video games, and we have the breakdown of their grades. So this is a two-way table. You might remember two-way tables back from section 2.1. And in a two-way table, we basically have two categorical variables, one that's represented by the columns and the other one that's represented by the rows. And as we look at this data, we can see that there's lots of things we could be comparing. Like we could compare the proportion of kids who get A's and B's for kids who played games or who've never played games, or we could compare the kids who got D's and F's for kids who played games and never played games. And it's tricky to kind of wrap your brain around, okay, well, what kind of comparison should I make to know if playing video games affects grade average? And that's where this overall test is going to come in. It's going to look at this and say, okay, is there any differences here? Does playing video games, is it associated with different grades? So the overall test that we're going to be looking at is called the chi-square test. And specifically, it's called the chi-square test of association. You might have noticed that we're skipping over section 7.1 and we're only doing section 7.2. 7.1 is another variation of this chi-square test, but I feel like the one in section 7.2 is the one that you're going to run across more frequently, or that's going to be more helpful to you. And we only have time to cover one of those sections, so I'm doing section 7.2. So it's called the chi-square test. Chi is a Greek letter. It kind of looks like a really fancy looking X. If you write it out in the English language, it would be CHI square. So, but it's not the chi test. So when when you call me up to ask me questions, don't say, hey, I'm having trouble with the chi, because I will just laugh at you. So it's called chi, it's Greek letter chi-square test. And what this chi-square test is going to do is it's going to compare the observed counts in a two-way table to the counts that would be expected if the null hypothesis were true. Looking back at our table here, this is our two-way table, and these numbers that we're looking at right here in the table, these are the observed counts. This means this is the data that we actually collected. So when we interviewed these kids, then we found out that there was 736 that played video games and got A's and B's. And what this overall test is going to do is it's going to say, okay, we saw that there was 736 kids in that group, but how many would we expect to see if there was no association between video game playing and grade average? So when we write the hypotheses for this chi-square test, it's going to be a little bit different than how we've been writing hypotheses in the past. In the past, we've written them always about our parameters. And this time we're going to kind of take a step back and look at this from like a broader perspective, in the fact that looking at our table, again, what we're really comparing here is two categorical variables, grade average and whether or not you've played video games. So this is really like the counterpart to when we looked at correlation. So if you remember when we looked at correlation, we had two quantitative variables, and we wanted to find out if there was a relationship between those two quantitative variables. Well, we can't compute correlation for categorical variables, but we can do this chi-square test, and that's going to help us know if there is a relationship between these two categorical variables. So when we write the hypotheses, we say null hypothesis. There is no relationship, or using the word association is also okay, between the row variable and the column variable. That should be an and. And alternative hypothesis is that there is a relationship or association between the row variable and the column variable. Now, of course, when you write this for an actual problem, you're going to fill in the name of the row variable and the column variable. This is just the generic way that we're going to write the hypotheses for this chi-square test. So for our example here, and I should point out that if you're using the notes pages that I made for you, the first page is going to have kind of the general where you just write down the formulas and how to write the hypotheses, and then the backside goes along with this example that we're looking at. And you might not need to kind of flip back and forth, because we're going to kind of toggle back and forth between showing you what the formula is and then actually using the formula in an example. So same thing with like the hypotheses. So you on the front side, where it talks about the hypotheses for the overall chi-square test, then you want to write down like this general format here. But then on the actual example for the video game data, then you want to write down this one. So here I have these two categorical variables, grade average and whether or not people have played video games. So my null hypothesis is no relationship between playing video games and grade average. And the alternative is that there is a relationship between playing video games and grade average. All right, so let's talk some more then about this overall test, this chi-square test. So this is the formula for the test statistic for that overall test. And what we're going to be doing is we're going to be comparing the observed counts in each of our cells to the count that we would expect if the null hypothesis is true. Remember, null hypothesis said no relationship, no association between those two. So if that was really true, this is the counts that we would expect in those cells. So this funky looking symbol here is a summation sign. So that just means that we're going to add them all up. So for each cell in our table, we're going to do this computation, the observed minus expected divided by expected. Sometimes people like to freehand this, or shorten it, I should say, not freehand it, by taking O minus E squared over E, as long as you know what that O and E stand for, observed and expected. When we look at our table, we're going to call it an R by C table. R is the number of rows and C is the number of columns. And we only count the rows and columns that are associated with actual data and not, so if there's any totals, rows, and columns, we wouldn't count those when we're counting the number of rows and the number of columns. So we look at an R by C table, so number of rows by number of columns, and the degrees of freedom, which we'll talk about a little bit more in a second too, are going to be equal to the number of rows minus 1 times the number of columns minus 1. So on your paper, when you're writing down this information about the chi-square test, where it says degrees of freedom, then write degrees of freedom equals R minus 1 times C minus 1. All right, and then the condition for using this chi-square test is that the expected count is at least 5 in each cell. So where it says condition on your paper, then write down this. So we want all the expected counts to be 5 or more. All right, so now we kind of have the formula. We know a little bit where we're going with this, but first question is, how are we going to compute this expected count, right? The observed count is given to us. That's our data that's in the table, but how are we going to figure out this expected count? And we have a formula that we can compute expected count with. And that looks like this. So this is how we're going to compute the expected count. So for each cell in our table, we're going to take the row total times the column total and divide that by n, which is our sample size or the overall table total. You can think of it that way too. And again, we're going to have to do this for all the cells in our table. So there's kind of a lot of calculations involved in this chapter. They're not difficult calculations, but they're going to be a lot of repetitive calculations. We're going to do the same thing a whole bunch of times. All right, so again, on your page, where it says compute the expected count by, if you're using my notes page, then make sure you write this formula down for computing the expected count. All right, and now we're going to take a look at this with our example that we're looking at here with these grades and video games. All right, so first step is going to be to compute those expected counts for all the cells in our table. So I'm going to start right here with this first cell. I have kind of a little naming system, I guess you could call it. I call it, well, first I call them E, right, for expected count. And then my numbering system is the first number here in the subscript is the row and the second one is the column. And there's no specific magic to this numbering system. It's just the one that I like. If you don't number yours at all, that's probably fine too. I just like to keep track of mine. It's my OCD side coming out. So E11 would be the first row and the first column here, this one here. So to calculate the expected count, I'm going to start with, so I'm in this cell right here, and I'm going to take the row total, which is 1379, times the column total, which is 941, and divide that by n, my table total. So I'm going to have 1379 times 941 divided by 1808. I get 717.72. And if you have your calculator with you, definitely do all these calculations along with me. It'll help you remember how to do them later. So I like to put it up here in my table too. So I'm going to have 717.72. Okay, so what this means is that when I did the study, there was actually 736 kids who played video games who got A's and B's. But if the null hypothesis is true, that there's no association between grade average and playing video games, I would have expected to see 717. Okay, so these expected counts basically take our total number of people here and redistribute them as if the null hypothesis was true. Okay, now I'm going to move on to my second one here. So this is still my first row, but it's my second column, so I call it E12. So I'm on this one, and I'm going to take the row total, which is 1379, times the column total of 594, and divide that by 1808. So 1379 times 594 divided by 1808 gives me 453.06. So So that one I've got 453.06. Okay, now I'm going on to the next one. So this one is still my first row. Now we're in my third column, so I call it E13, and my row total is 1379, and my column total is 273, and I'm going to divide that by 1808. So 1379 times 273 divided by 1808 gives me 208.22. Now I've done the whole first row. I'm ready to move on to the second row here. So this second one, I call that E21, second row, first column. So that would be 429 times 941 divided by 1808. So I'm going to do that one, 429 times 941 divided by 1808 gives me 223.28. All right, next one here, E22 by my naming system is 429 times 594, so row total times the column total divided by n, which is 1808. So 429 times 594 divided by 1808 gives me 140.94. All right, finally I'm to my last cell here. So I'm going to take 429 times 273 divided by 1808. And I get 64.78. All right, so now I've gone through, I've calculated the expected counts for all the cells in my table. And if you ever need to figure out how many cells you should be doing this for, if you look at the number of options for each of the categorical variables and multiply those together, that's how you figure out how many you're going to end up doing this for. So for grade average, we had 3 options. For video games, we had 2 options. So 3 times 2 is 6. That means that there's 6 cells with actual data in them, and I'm going to be looking at 6 expected counts as well. And if you add up all your expected counts, it should always add back up to n, the total sample size. So now I've got all my expected counts. There they are in prettier form. And now I've got them written up there in my table. And now I'm ready to start computing my chi-square statistic. Okay, so remember the chi-square was the sum of the observed count minus the expected count squared divided by the expected count. So we're going to do this computation for each of the 6 cells that have data in them in my table, and then we're going to add them all up. So first we just write it all out, then we do each of the 6 pieces, then we add those 6 pieces together. So starting with this first cell here, my observed count is 736, and I'm going to subtract the expected count, which is 717.72, square that difference, and divide by 717.72. Okay, same thing for the next cell. So this one I'm going to have 450 minus 453.06, square that difference, and divide by the expected count of 453.06. Plus, now I come over here to the next cell, I'm going to have 193 minus 208.22, square that and divide by 208.22. I ran out of room. If I was on like a big long chalkboard, I could keep going, but Zoom's cutting me off. So coming to the next line, but really it's all part of the same equation. So this next one, I'm going to have 205 minus 223.28, square that and divide by 223.28, plus, now I'm in the middle on the bottom here, so I have 144 minus 140.94, square that and divide by 140.94, plus, now I made it to the last one here, so I'm going to have 80 minus 64.78 squared, then divide that by 64.78. All right, so I've written out the whole equation to compute my chi-square test statistic, and now I'm ready to do each piece. So each of these little chunks, I'm going to compute those, and then I'm going to add those 6 numbers together. So starting with the first one here. So I have 736 minus 717.72, which gives me 18.28. I square that and then divide that by 717.72. And I get 0.466. All right, that was this first chunk. Now I'm going to do this second chunk here. So I have 450 minus 453.06, which equals negative 3.06. Then I square that and divide it by 453.06, which gives me 0.021. Plus, okay, now I'm coming over here to the third one. So I get 193 minus 208.22. Square that and divide by 208.22. And hopefully you're all following along on where these numbers are coming from. But if anybody's confused, feel free to jump in and ask questions. Like I said, I don't think they're really that hard, but they're kind of tedious because you have to do a lot of them. So it's very repetitive. All right, the next one now, I'm down on this second row here. So I'm going to have 205 minus 223.28. Square that and divide by 223.28. And I get 1.497. Next one, 144 minus 140.94. Square that and divide by 140.94. And I get 0.066. And if I do something wrong and we get a different answer, then feel free to let me know that too. All right, and then my last one here, I've got 80 minus 64.78. Square that and divide by 64.78. And that gives me 3.576. All right, so now I've got all these individual pieces here. Now I can add all of those together to get my final chi-square statistic. So this part right here, this intermediate step where I just have these 6 numbers added together here, we call these the contributions to the chi-square. So this is basically each cell in the table, it's that cell's contribution to this chi-square statistic. And we're going to see in a minute when we look at finding the p-value and things that the bigger your chi-square statistic, then the smaller the p-value, the more evidence that you have. So it's going to be helpful later on. This is kind of a preview of coming attractions here, but to be able to know what the different contributions to the chi-square statistic are. So I'm going to write that off to the side here a little bit. So I'm just going to write contributions to the chi-square. All right, so now I'm going to add all those contributions together to get my final chi-square value. So I get 0.466 plus 0.021 plus 1.113 plus 1.497 plus 0.066 plus 3.576. And when I do that, I get 6.739. All right, so that's 6.739. That is my test statistic. And just like in chapter 6, a test statistic is going to be useful for helping us to figure out our p-value. So you remember in chapter 6, we find our test statistic and then we use either the normal distribution or the t-distribution to help us figure out our p-value. But this test statistic, the chi-square test statistic, does not follow a normal or a t-distribution. Instead, it follows a chi-square distribution. So we're going to look at the chi-square distribution. Here's my whole thing with a few more decimals and looking a little prettier. All right, so let's talk about the chi-square distribution, some characteristics of the chi-square distribution. And first of all, it takes only positive values. So that's something different than the normal or the t. And if you look at how we come up with our chi-square statistic, we're taking an observed count minus an expected count squared divided by an expected count. So anytime I square something, it's going to be positive. And then an expected count is a count. We can't have like a negative. We can't be expecting like -3 people to be in there. So that's always going to be positive. So you can see that when I do this calculation, it's always going to be positive. So the chi-square distribution only takes positive values. And partially because of that, then the chi-square distribution is also not going to be that beautiful symmetric bell shape that we're used to seeing with the normal and the t. Instead, it's going to be a distribution that is skewed to the right because it's bounded by 0 because it has to be positive, and it's going to be skewed to the right. So when we're looking for p-values, the p-value is always going to be in the right tail. So I'll write that here, p-value always in the right tail. We talked about this a little bit already, but degrees of freedom for the chi-square distribution are equal to the number of rows minus 1 times the number of columns minus 1. And the conditions for using this chi-square distribution as a model are going to be that all the expected counts are greater than or equal to 5. So looking back here at our table, we can figure a couple things out here. First of all, degrees of freedom, we said were equal to number of rows minus 1 times number of columns minus 1. So how many rows are in this table? What is R equal to? How many rows? You might remember at the beginning of class when we talked about how to count how many rows there were, it's the same as the number of options for that categorical variable. So how many options were there for played video games? 2, exactly. So there's 2 rows. And then how many options were there for grade average? 3, right. So we're going to have 2 minus 1 times 3 minus 1. Okay, so remember when you're looking at the number of rows and the number of columns, the totals, any kind of summary rows and columns are not included, just the middle ones. Okay, so that ends up giving me a whole 2 degrees of freedom. So I have 2 degrees of freedom for this problem. All right, so to find my p-values, there's a couple different ways to find p-values for the chi-square. One way is to do a randomization distribution, which we're not going to do this one in our class. But when we go into StatKey later on, you're going to see where that would come up. So I don't want you to be confused by it. We're not going to do it in our class, but it is a possibility. The one that we're going to be using is option number 2. We're going to use the StatKey theoretical chi-square distribution to find our p-value. And a third option is to use the table. But since we're forced to do our tests online and everything anyway, instead of in the testing center or something like that, then we're not going to use the table. But some semesters I do use the table. So let's go into StatKey and we'll look at how to do that in there. So first I got to open up a StatKey window. Okay, so in StatKey down here where it says theoretical distributions, we've looked at normal, we've looked at t, and now we're going to look at this chi-square. So I click on the third option over where it says chi-square. I'm going to tell it how many degrees of freedom I have, which in this case I have 2. You'll notice for chi-square tests the degrees of freedom are not very big. And when we do this test, like in the past, we talked about one-sided tests, two-sided tests, but when we're looking at this overall test, it's really like a multi-sided test. So I'm just going to click on right tail. You'll always click on right tail, never left tail or two tail when we're doing the chi-square distribution. It's too bad. I guess StatKey just wants you to be able to test you and make you make your own decision, but they should really just take those 2 off because you don't ever need those. You only ever need the right tail. So you click on right tail, you're going to put your test statistic in this bottom box here, 6.739. And when you do that, this floating box is your p-value. So I'll just arrow to what those are. So this one was our test statistic. Oops, I'm not very good at spelling today. This one is our p-value. Okay, the degrees of freedom here came from the number of rows minus 1 times the number of columns minus 1, and we're always going to use right tail for a chi-square. All right, so we did all that work. We finally got our p-value, this 0.034. So let's go back and figure out our conclusion for this test. So we figured out we had 2 degrees of freedom, 0.034 was our p-value. So our conclusion, we reject the null hypothesis. And when we reject, that means we have sufficient evidence for the alternative. So just like before, I'm going to say reject or fail to reject. If I reject, that means I have sufficient evidence for the alternative. If I fail to reject, that means I do not have sufficient evidence for the alternative. So this time I rejected, meaning I have sufficient evidence, and then I just write out the alternative hypothesis. So the alternative was that there is a relationship between video game playing and grade average. So this is my conclusion based on that overall test, the chi-square test. But, okay, if you remember in our strategy that we talked about at the beginning of class, we said, okay, our strategy is do an overall test. And if the overall test is significant, then step 2 is we need to do some follow-up analysis to see where the differences are. So we're not quite done with this problem yet. We need to do that follow-up analysis. And this is where those contributions to the chi-square statistic come in. Okay, so for our follow-up analysis, what we're going to do is, and there's a place for you to write this down on your notes as well. So first, we're going to look at each cell's contribution to the chi-square statistic. That was the part that we highlighted before, each of those, in this case, each of those 6 numbers that we added together. We're going to find the biggest ones, okay? Because the bigger your chi-square statistic, the smaller your p-value, the more evidence you have. So whichever cells are making that chi-square big are going to be where the action's happening, basically. So we're going to find the biggest contributors. We're going to look back at those cells in our two-way table, and we're going to compare the observed and expected counts in those cells and try to figure out, kind of from more of a broad perspective, what's going on? What kind of relationship do they suggest here? All right, so we're going to do that with our video game and grade average data here. So here was all of the contributions to our chi-square statistic. These were all the numbers that we added together. And you can see that my biggest ones were here and here. Okay, those were the biggest ones that we found. So if I look back at my table, those numbers came from these 2 cells here that I've got circled. So now I'm going to look at the observed and the expected counts and see, okay, well, what's going on here? So for this first one, okay, I observed 205 people who never played video games that got A's and B's. But if there's no relationship between grade average and playing video games, I would have expected to see about 223. So there were fewer kids who got A's and B's who never played video games than what I would have expected to see. Looking at my other one here, I saw 80 kids that got D's and F's when I would have expected to see about 64, 65 kids. So there was a lot more kids that got D's and F than what I would have expected to see there. So it seems like not playing video games is being associated with worse grades, and playing video games then is associated with higher grades. And we can kind of see that here as well, looking back at those. So it looks like we saw a lot more kids get higher grades who played video games than what we would have expected. And the kids who didn't play video games were seeing lower grades than what we would expect. Okay, so now we're just going to try to assimilate all that information and come up with some like grand conclusion based on our follow-up analysis. So our first conclusion based on the chi-square statistic was that we had evidence of a relationship, and now our conclusion based on the follow-up analysis that we just did, okay, is that playing video games is associated with higher grades and not playing video games is associated with lower grades. All right, so based on this study and all of our analysis that we've done with this, does this mean that playing video games causes higher grades? Can we help kids out just by making sure everybody has a great gaming system at home? Just play a little Mario Kart in between studying and you will be good to go. No, how come? I mean, we just saw it's associated, not playing video games is associated with lower grades, playing video games associated with higher grades. What kind of study was this? This was an observational study, right? So at the end of the day, we can say that, it looks like in our study that there was an association, but remember, association is not always causation. So there could definitely be some lurking variables in here. So we cannot say that one causes the other. We would want to do a designed experiment for that. I'm sure that my kids would be happy to volunteer for that too, as long as they got put in the video game group. All right, so let's look at, that was us doing all those computations by hand, but there is also a way to make StatKey do all those hard calculations for us as well. And I do want you to know both ways. And on the exam, remember, this is not on test 4, which is due on Tuesday. This is going to be part of test 5. But on that exam, you will be expected to do both. You'll need to figure out how to read computer output and understand what it's giving you there. You'll also be expected to do some of these calculations by hand. So in your homework, especially like the Wiley Plus homework, feel free to do it either way, do it by hand or have StatKey do all the calculations for you. Just be aware that you need to know how to do it both ways. So I'm going to show you how we would do this analysis in StatKey. So in StatKey, then at the very bottom here where it says more advanced randomization tests, this second one here says chi-square test for association, and that's what we're doing today. So don't do the first one, goodness of fit. If you feel bad that we skipped that one, it's in section 7.1. You can go back and read it. But this one is test for association. So I'm going to click on that. And the hardest part here is just getting our data put in. And to do that, there might be some data sets from Wiley Plus that are already in there for you, or that you can upload from their data file thing. But sometimes you're going to have to type these in by hand. And so if you click on edit data, you can kind of see what it looks like. It basically looks like our two-way table, but kind of everything's separated by commas. So the easiest way that I've found to get the data in there properly is to first put it into a spreadsheet. So I'm going to open up Excel to put it in there. If you don't have Excel, you can do this on a Google Sheet. You can do it in whatever the Mac version of Excel is. Any of those will work. And what I'm going to do in here is I'm going to type in my data, and I just want it to look exactly like it did on my original table, but with no totals, rows, or columns. So I'm going to have A's and B's here, C's, D's, and F's. And then I'm going to put played games and never played games. And then I'm going to put in all my numbers. And remember, the number of numbers that you should have should be, if you take the number of options for variable A and the number of options for variable B and multiply those numbers together, that tells you how many cells of actual data you have. So I've got 736 there, 205, 450, 144, 193, and 80. Okay, so now, if you hold up your chart from our example sheet and you look at my computer screen in Excel, you can see that they look the same, except for we don't put any totals in here. So now I'm just going to highlight that whole block of my table there, hit Control C or copy it however you copy on your computer. And I'm going to go back to StatKey. And in StatKey, I'm going to delete everything that's there, and I'm just going to paste in what I had on my spreadsheet. So as long as I make it look great in my spreadsheet, I can copy paste it in here, and it should work just great. Down below, when you do it this way, you don't have raw data, so you make sure that that box is not checked. And then I did have a header row because I labeled my column, so I leave that box checked. So now when you click OK, then this little box over in the corner should be the full table that we had before, this time including the totals, rows and columns like you see, and you can see our total number 1808 there. And right above the box, if you look, what does it give us? That chi-square statistic. So remember how long it took us just to calculate that number? And all we had to do is like cut and paste and bam, StatKey did it in like half of a second. So that's pretty great. So that's how we get it to calculate the chi-square statistic. But then, of course, we know that for our follow-up analysis, we need to know the contributions and all that kind of good stuff. If you click on where it says show details here, then it brings up another table that has all that extra information in it. So this table has multiple things. They're color-coded. The top black number is the observed count. The middle green number is the expected count, and the bottom blue number is that contribution to the chi-square statistic. So if you were having StatKey compute your chi-square for you, and then you needed to do the follow-up analysis, you would click on that show details, you would look at these blue numbers, look for the biggest ones, and then you would know which cells to look at. And it's really handy that it's organized this way, because then you don't even have to go back and forth and say, okay, well, which cell did that come from? Because it's already organized by the cell. So you know exactly which cell that it came from. All right. Notice that we have all this stuff over here on the left side for the randomization dot plot. We are not doing that part in our class. So don't touch anything with that. Do not click on any of the generate samples buttons or any of that. We're only using StatKey to compute our chi-square statistic for us and all these other fun details. Now you might have noticed that in all its wonder, StatKey did compute the chi-square. It did give us all these extra details, but it left out one. It left out the p-value, which I personally find is really annoying. I feel like, hey, StatKey has the capability. They could have just put p-value and put it right up there for us, but they did not. So if you're having StatKey compute your chi-square, you still need to find the p-value the same way that we did when we did everything by hand. So I would write down my chi-square value, I would calculate my degrees of freedom, and then I would have to go to the other part in StatKey here, the theoretical chi-square distribution, and figure out my p-value the same way I did by putting in the degrees of freedom. Now I forgot my value, it's 739, I think. And hit OK, and then I would get my p-value like that. So the other part of StatKey does not give you the p-value. You still have to go into the theoretical distribution part and be able to find that. All right, and I know that you might forget all this StatKey stuff. So on your notes page, I put some detailed instructions on how to do the chi-square inside of StatKey. So when you get stuck on your homework, then you can read through that and remember how to do that.